Okay, welcome to topic 3.2, and this topic looks at the interactions between molecules. And the clear learning intention today is that the physical properties of molecules depends on really like the strength of the intermolecular forces. All right. So going on, there's really two type of electrostatic forces present in a lot of materials. Firstly, we've got our intramolecular forces. All right. All right. Now we looked at covalent bonding, ionic bonding, metallic bonding. Those are known as your intramolecular forces, and I'm just going to put an underline between the tra section. And what is that? That's the force of attraction between atoms in a compound. All right. So the force of attraction between atomic particles in a compound. And we've got a couple examples. Ionic bonding and covalent bonding as well. All right. And if I can give an example, if we look at CO2, there is our covalent bonding there. Okay. Or if we look at another example, HCl, and just remember this is our delta negative, this is our delta positive side, so electrons are probably pushed a little bit, well not probably, but they're pushed a bit more to this side here. All right, that is another example of a covalent bond as well. Okay, so that's intramolecular forces. All right, they're also quite strong depending on what they are. Ionic being the strongest, covalent's a lot less strong. Metallic bonds are very strong as well. All right, the next one that we'll look at is intermolecular. Forces. I'll just sort of have it around there. Okay, now what is an intermolecular force? It's an electrical force between two molecules this time. So it's not between atoms in a compound, but it's the electrical force between two molecules. Okay. All right. Now, some examples that we can look at is hydrogen bonding, dipole interactions as well. and London dispersion forces. All right, one other thing, and I'm just going to put it in a different color now. Intramolecular forces, which we looked at before, they're also known as primary bonds as well. Or primary bonding. Whereas on the other hand, intermolecular forces are known as secondary bonding as well. Okay. I'll just put another little side note here. Weaker than primary. Okay. All right. Going on with intermolecular force, I just want to give you a bit of an image as well. That sort of sums up these two slides. Let's look at H2O. Okay. Remember, oxygen's there, hydrogen, hydrogen, and I'll draw oxygen here, hydrogen, hydrogen. Now what I've got to draw in next is our dipoles. So this would be delta negative. This too would be delta negative. Whereas this here would be delta positive. And this too would be delta positive. Likewise with this here. Okay. All right, before I talk about intermolecular forces, I'm just going to say this, and I'll put this in a different color. Let's go purple. What was this here known as? The interaction between the oxygen and the hydrogen where they're sharing electrons to form a bond. Yeah, this was an intramolecular interaction or force. Now, let's go yellow this time. What a intermolecular force would be, it's an electrical force between two molecules. So here we go. The hydrogen and the oxygen are going to weakly attract one another to actually form an intermolecular force, which is actually quite weak. Okay, and I'm just going to put that there. Intermolecular force. All right, that image, I'm going to put a little box around it. That is a really good image to actually show what the difference is between an intramolecular force and intermolecular force, okay? And this intermolecular force is also known as hydrogen bonding too. Now we can see there's that opposite in electronegativity with the dipoles. That's where there's that weak interaction between the two, which forms a secondary bond, okay? Make sure you copy that into your book. That's a really, really key pivotal image to have. All right. Now, the next thing I'm just going to sort of note down here too is the physical properties such as melting point and boiling point are really dependent on the strength of the intermolecular forces in a material. And I'll just make a little note with a little asterisk here, or a little star here, but physical properties, as I said before, such as melting point and boiling point, are dependent on the strength of secondary bonding, which is known as, your intermolecular forces. All right. going on. Okay. I do like to have a nice little like layout of this all as well, and I'm just going to sort of put this into play here. So at the top, let's go in a different color. Let's go with a purple. All right. We're going to have chemical bonding. Okay. Now that's what we just spoke about earlier. That's going to branch out into two directions here. Okay. So, in two different colors, we've got intra molecular bonding, and on the other side we've got intermolecular bonding. Okay. All right. Now, going on, let's go back to purple, to the next thing. All right. This is going to determine, oh, let's go with the red color again, just to sort of keep things consistent. This here determines chemical properties, whereas this here sort of determines physical properties. Okay, back to purple. All right, we can see there's two types, and remember intramolecular was between atoms in a compound. Okay, intermolecular is between molecules. Okay, and we've got ionic bonding, and we've got covalent bonding as well. And if we go down further, we've got our polar and non-polar molecules. All right. I could put a bit of a description here. Now, just remember with ionic bonding, bonds are formed between ions. Covalent bonding, bonds are formed between nonmetals. I'll just explain that now as I'm going through it. With intramolecular bonding, it's the force of attraction within a molecule, okay? And then on the other side, we have intermolecular bonding. Determines physical properties like we said earlier. It's also the force of attraction between two or more molecules. I know I just showed two earlier, but it's two or more. Okay, and we've got three different types, which I said one a little bit earlier. Okay, the first is dipole interactions. The next is hydrogen bonding. And finally, we've got London dispersion forces. Okay, and let's look into these types of intermolecular bonding. All right, first one that we're going to look at is dipole. Okay. Dipole interactions. Okay. And just ask yourself again, looking back at this, all right, which type would it be? And again, we can just say intermolecular forces. Okay. All right, with dipole-dipole forces, it's observed in polar molecules due to their permanent electric dipoles. Okay, so I'll just say it's observed in polar molecules. All right, and that's due to their permanent electric dipoles. There's also a mutual force of attraction between the positive pole of one molecule and the negative pole of the second molecule. All right, and I'll just say that is also mutual force of attraction between two oppositely charged poles. As well. Gee whiz, I can't spell here. I hope you spelt mutual correctly. Mutual. All right. An example of which I'm just going to show HCl. All right. And I'll show HCl over here, and I'll show another HCl. Now just remember, H would be delta positive in this scenario. This would be in a polar molecule, by the way, so these are polar molecules. All right, and Cl would be delta negative or electronegative. All right, so firstly, as I said, it's observed in a polar molecule. We can see HCl is a polar molecule as well. All right, there would be dipole-dipole interactions between the Cl and the H. Okay, and if I draw another one down here, HCl, we can see that there would be an interaction there as well. Okay, so if I draw just two random, randomly shown dipoles here you got delta positive bound to delta negative. And again, you got delta positive bound to a delta negative. There is that dipole-dipole interaction between there. And I'm just going to put a side note here that this is a dipole interaction. All right. Key thing, observed in polar molecules, and it's a mutual force of attraction between two oppositely charged poles. Okay. And what are your two oppositely charged poles? You've got delta positive and a delta negative. All right, going on, that's dipole-dipole interactions. Hydrogen bonding is very similar, which we'll go through next. All right, hydrogen bonding. And looking at this, I'm just going to go through this one next. We can see hydrogen bonding as well is very similar, as I said, to dipole-dipole, but hydrogen bonding is actually a stronger version of dipole-dipole forces. All right. Now, with hydrogen bonding, we'll just go a bit further down. Hydrogen bonding occurs when hydrogen is bonded to any of the three most electronegative elements. So I'm just going to make a note here. H bonding occurs when hydrogen is bonded to the three most electronegative elements. Those being fluorine, fluorine's the most electronegative, oxygen, and nitrogen. Fond. All right, that is how hydrogen bonding is formed. So let's look at, for example, HF. Okay, so HF would be the most electronegative. So we would have hydrogen here, fluorine there. Okay, and definitely hydrogen will be delta positive, and fluorine would be delta negative. And we'll draw a few more of these. HF, HF, and let's put a HF here. All right, and let's put another HF here, and let's go. So there'll be some hydrogen bonding going on there, hydrogen bonding going on there, hydrogen bonding going on there as well. Let's put another one over here. We can't really get it to go again. And there would be some hydrogen bonding going on here too. And I'm just going to get rid of that one there. Okay, just to show how that would look. All right. All right. The next thing I just wanted to say is that with HF, that would be the most electronegative. This would also work with NH3. It also works with H2O. I'll just show a few H2O molecules. And that would work there, that would work there, okay? And we can see that H would be delta positive, oxygen's delta negative, same thing goes here, delta positive, oxygen's delta negative, and they're forming those hydrogen bonds. All right, and that's hydrogen bonding. As we said earlier, though, you know, dipole-dipole interactions observed in polar molecules. Hydrogen bonding's definitely observed in polar molecules. And, you know, fluorine, oxygen, nitrogen, the three most electronegative three elements there are. All right, it is observed in all those. The next thing I just wanted to go through, just going back to not hydrogen bonding, sorry, but dipole-dipole interactions. There is a trend in the boiling points. Like, say, if we look at group 7 elements, there's usually a bit of a trend in boiling point as well. So pretty much just looking at something such as, just going to go back to here, going through boiling points of dipole interactions. So we could see that for like something like HF and HCl. So HF, that's in, you know, group 7 period 2. HCl, group 7 again, but period 3. All right. What does that mean? Well, the boiling point for HF is a lot higher than what it would be for HCl. So I'll just write boiling point for HF higher than HCl. Okay, why, you may ask yourself? Well, the dipole, and this does sort of connect a little bit to hydrogen bonding too. Interaction between H from one molecule and Cl from the other HCl molecule is weaker than the hydrogen bonding in HF. Alright? And the same would go like with another element in group 7 further down, okay, such as bromine. Alright, that would get even weaker after that. Alright, going on to the next one, I must just verbally say though that boiling points of a lot of molecules that have hydrogen bonding, alright, is going to be considerably higher than some of your dipole ones because of that as well, meaning there's just more energy needed to break those bonds and hydrogen bonds down. All right, the last one that we looked at a little bit earlier are London dispersion forces. I don't mind if you just call them dispersion forces, all right? Now, this is the weakest, all right? This type of secondary interaction really exists between non-polar molecules. So the secondary interactions or the secondary bonding exist between non-polar molecules. All right, and as I said earlier, it is a weaker interaction as well. All right. Going on with this, so there will be, because it's a weaker one, there will be temporary dipoles which are caused by the movement of electrons in a molecule as well. With this, there is an instantaneous dipole moment due to that asymmetry as well, and there's an induced dipole in the second atom. All right. As I said, the strength of the dispersion forces depends on the size and shape of the molecule. All right. So strength depends upon the size and shape of a molecule. All right. Now, larger molecules have a larger dispersion force than smaller molecules, meaning it has a higher boiling point as well. So I'm just going to note that larger molecules have larger dispersion forces than smaller molecules. Therefore, will have a higher boiling point and melting point too. And dispersion forces as well, they were found. Now, the reason why I do say London dispersion forces, they were found by a scientist named Fritz London, okay, who introduced the concept of dispersion forces too. Now, going on with dispersion forces, I'll just get a bit of an image that is good to go, so you can visually see it. And you can sort of see something here. Okay. All right. So now, so you have a symmetrical distribution of electrons. Here. All right. That, let's just say this is known as atom 1. All right. Got your nucleus, and let's say the electrons be carried around that way. Okay. Now, what happens in London dispersion forces, the next step pretty much, is that now we've got two atoms, atom 1, atom 2, and what's going to happen, there's going to be induced dipole due to that asymmetry, all right? And that will sort of look such as this. The electrons will sort of go to one side, all right? And protons will sort of go to the other side, all right? And there'll be that binding between the two. And you've got, and as you can see here, you've got an induced dipole in the second atom, all right, and an instantaneous dipole moment due to asymmetry. Symmetry. It's not double S, it is 1S. All right, that's it for today's video. It's a bit longer than I expected it to be, and it's a bit longer than what I really wanted it to be too. But pretty much, I know hope this makes it look a bit easier. If I can make it look even more easier, it's sort of, let's try and keep it similar to, you know, what I showed earlier. All right, and there's that interaction there, okay? Because it's non-polar and because of the symmetry, there's going to be a bit of an uneven distribution of the dipoles, all right? And it does form like a London dispersion force. All right, hope this helps. And after you're done, go on with question 9 through to question 12 from the booklet.